everybody. So just now we have done with the pure semiconductor, that is extensive semiconductor, and we found that the problem with the pure semiconductor is that number of electrons available in a conduction band and number of hole available in a valence bands are very less. So therefore we need to increase the number in order to increase the conductivity. All right. So now we would like to discuss the extensive semiconductor, that is impure semiconductors. That this is how we can able to increase number of electrons and a hole, so that semiconductor can be used in a much better way. All right. So now extensive semiconductor is what we call as the doped semiconductors. So that means we are going to put some other atoms other than semiconductors, so that we can increase number of electrons in a conduction bands and we can increase number of hole in a valence bands. So this is how it goes. When a small amount of suitable impurities, that is a few part per million, that is ppm part per million, is added to the pure semiconductor to increase the conductivity of semiconductor. That is, objective is to increase the conductivity, and we will see how it increase conductivity, right? And however, look at here, we are not going to put so much impurity, right? The amount of impurity which we are going to add is what we call as the part per millions. All right, the amount is very small compared to silicon atom, but the number would be very large. Why? Because let's say if I have silicons, let's say I have a silicon atomic mass is, let's say it is of 28 molar mass is 28 gram. If a silicon molar mass is 28 gram, 28 gram of silicon contains 6 into 10 raised to the power 23 silicon atoms, right? That is Avogadro's numbers. Alright, so what about part per millions? Part per million means I am going to divide this by 1 million, right? So therefore, how many electrons now available, right? How many impurities are there? 10 raised to the power 17, right? So 10 raised to the power 17 silicon impurities are available in case of extensive semiconductor. However, compared to the number of a pure semiconductor, it is less. However, the numbers are more wide. Why? Because number of electrons, number of silicon available in a silicon atom available in a 1 molar mass is very large number. So that's the reason, right? So this is what we have, and now what do you mean by doping? Right, the doping is how to make silicon's impurities. All right, while we were doing the dopings, the doped semiconductor has to be so much used, right? So therefore, we are going to do it deliberately. Purposely we are going to add desirable impurity. We are not going to put any kind of impurity, right? We are going to put desirable impurities. Deliberately we are going to put desirable impurity to a pure semiconductor. That is what we call as doping. The doping is a process of the deliberate addition of desirable impurity to a pure semiconductor, right? So now, how many types of impurities are there? So we discussed the 2 types of impurity, and impurities are what we call as a dopant. Dopants are what we call as impurity. Dopants are equivalent to impurities, right? Dopant has to be of such that it does not distort. That's, you should keep in mind, right? You should not distort the entire crystal structure of silicon atoms, right? So that you should keep in mind. However, this dopant can change the conductivity, change the property of that crystals. However, it doesn't change the crystal structure. So that you should keep in mind. The 2 types of dopants are available, that is pentavalence Pentavalence, valency is 5, therefore it is called a pentavalence. And the phosphorus are normally used. And then trivalent, valency is 3. So normally we use is the boron and aluminum are used. Alright. So we have two types of doping impurity. One is a pentavalence and another one is trivalent, right? Based on this impurity, based on these dopants, we divide extensive semiconductors. We divide a semiconductor, extensive impure semiconductor into two semiconductors. P-type semiconductor and N-type semiconductors. Alright. So we have two types of extensive semiconductor, and that is based on types of dopant you use. So we have two types of dopants, pentavalent dopants and trivalents. Alright, and the pentavalent normally we use the phosphorus, trivalent normally we use the boron and aluminum, right? So based on this impurity, we have two types of impurity, two types of extensive semiconductor. One is what we call as P-type semiconductors, another one is what we call as N-type semiconductors. So what is N-type semiconductors? So in case of N-type semiconductors, we use the pentavalence atoms. We use a pentavalence atom. In case of pentavalence atom, we have 5 electrons. 5 electrons available in a outermost shells. 5 electrons available in a valence bands. Valence electron. We have 5 valence electrons. Because of these 5 valence electrons, the phosphorus atoms, alright, the 4 electrons of the phosphorus atoms join with 4 other neighboring silicon atoms, and the 5th electron of the phosphorus atoms remain less bound to a phosphorus nucleus. So therefore, this would be having a higher energy. Why this would be having higher energy? This is less bound to phosphorus nucleus. 4 phosphorus electrons join with the 4 neighboring silicon atoms and forming a strong covalent bond, and a 5th electron, phosphorus electrons become less bound to phosphorus nucleus. So therefore this is having a higher energy, and this can easily get into a conduction band or in a lattice stage. So therefore we put this as a plus, and all others are there is no plus on the silicon. Why? Because silicon will be having 4 silicons. Alright, we will be having 4 plus silicon. We will be having 4 plus silicons. However, 4 plus silicon get neutralized with the 4 other electrons. Right. So this electrons, this electron, that electrons, that electron. So therefore, I say 4 silicon, and like this, that. You can remove this. You can remove this. You can remove this. However, in case of a phosphorus, 4 phosphorus silicon, 4 electron of a phosphorus atom join with the 4 neighboring silicon atom, and a 5th. Now phosphorus is going to lose 5th electron, and the 5th electron goes into a conduction band or in a lattice space, and now phosphorus become positive ions. 1 positive ion. So this is what we have. Alright. So therefore, this creates a free electron in a conduction band. This creates a free electron in a conduction band. If I add 1 million phosphorus atom in a crystal, in a silicon crystals, and 1 million free electrons are available in a conduction bands, and I create 1 million free electrons in a conduction band, and this increases the conductivity of external semiconductor, and this kind of a semiconductor is what we call as N-type semiconductor. This is what we call as N-type semiconductor. So therefore, when we use pentavalence, alright, when we use the pentavalence dopants, then what we get is N-type semiconductors. So this is what I have. when an atoms of a 5-valency element occupy a position of an atom in the crystal lattice of silicon, 4 electrons bond with the 4 neighboring silicons, while a 5th electron remains very weakly bound to its parent atom. As a result, the ionization energy required to set this electron free is very small. When even at a room temperature, it will be free to move in the lattice of a semiconductor. So that's what we talk about. So earlier, in case of silicons, so energy gap is 1.11 electron volt. Now it is reduced to 0.5 electron volt. Earlier, in case of germaniums, it is of 0.7 electron volt. Now it is reduced to 0.01 electron volt. So this at room temperature, these kind of energies are readily available. So all the electrons can push into conduction band. So this is what we call, and this is what we call as a donor energy level. And I mean, this sets a new energy level, and that is what we call as a donor energy. That I will explain you now, right? I'll explain you here, right? So this is what we have at a 0 Kelvin. This is valence energy band. This is conduction energy bands. Now I say this is a donor energy level, right? This is what we call donor energy level, right? So and this energy is very, very small energy gap. Energy gap is very small. That's the point. All right, that's the point. This is what this. So therefore, when I do a joggings, the entire semiconductor creates new energy level. That is what we call as donor energy level, and the energy gap between the donor energy level and conduction energy level is very small. And even at a room temperature, all the electron available in a donor energy level can get into conduction band. So that's the point. So this is what I have here. Example, I would like to give you this. This is what we have. Yeah, this is what we have. This is a phosphorus plus 5. All right, and this is the 5th electron of a phosphorus atoms, which is very less bound to a phosphorus nucleus, phosphorus atoms, and this can be easily pushed into a conduction bands, and that is what we call. So therefore, this is what we call as a donor core. Plus this is called a donor core. Why plus? Why? Because this lose 1 electron. Once it loses 1 electron, this creates positive ions, right? Positive ion. This is a fixed positive ion. This is fixed positive ion, right? This is what we have. Unbonded free electron donated by a pentavalence. That is a plus 5 valency atom. So this is what we have. So this is what we have in case of energy band theory, right? So look at here. Now there are two ways of creating hole and two ways of creating a free electrons. So now look at here. Temperature more than 0 Kelvin. At temperature more than 0 Kelvins, how many holes are created? 1 hole are created. Because of this hole, 1 electron are created. So this is a thermal, right? Thermal excitations. This is due to thermal excitations. And how many? 1, 2, 3, 4, 5, 6, 7, 8, 9. These 9 electrons are because of donor atoms. All right. So this is what we have, right? So now in a process, what we have is we have holes are available and electrons are available. Holes are available, electrons are available, and holes is less in number. Why? Because this is due to thermal excitations, and electrons are more in number. All right, this is due to thermal as well as doping. Thermal as well as doping. So therefore, in a process, what we say is that hole is what we call as a minority charge carriers. And electron is what we call as a majority charge carriers. This is what we have. All right, and this is for germanium. This is conduction band. This is a donor energy level, and this is valence energy level, right? Valence energy level and donor energy level. This is conduction energy level, and in a way, a conduction band has 10 electrons. 10 electrons in a conduction band, out of which 9 is due to donor atoms, and 1 is due to thermal excitations. So therefore we have a majority charge carrier is electron and a minority charge carrier is hole, right? So therefore what I call is this is, alright, this is what we have, and this is energy K, and for electron to excite from valence to conduction band is of very high energy is required. So this creates a one hole and one electron, and the rest of electrons due to process of doping. So this is what we have. Now we talk about p-type semiconductors. So in case of n-type semiconductor, the majority charge carrier is electron, minority charge carrier is hole, and the doping is pentavalence, and this creates positive donor ions. This creates positive donor ions. Alright, this creates positive donor ions, right? This creates positive donor ions, right? Look at here, I will show you this. This creates a positive donor ions. Positive donor ions. Alright. So majority charge carrier is electrons, and a minority charge carrier is a hole, and then the dopant is pentavalence, and this creates positive donor ion, right? So majority charge carrier. All right, this is what we have. So now p-type semiconductor. Now we talk about p-type semiconductor. Let's say I'll do a small n-type. All right, this is pentavalence. Pentavalent atom. This is donor is the dopant is pentavalence, and this is valency is 5 valency, and the majority charge carrier is plus electron, and a minority charge carrier is hole, and then it creates a positive ion, right? Donor positive ion. It creates donor positive ion. So this is what we see in case of n-type semiconductors. Now let's talk about p-type semiconductors. In case of p-type semiconductor, we are going to use trivalence. We are going to use trivalence atoms. Right? We are going to use trivalence atoms. So normally we use this a boron and a aluminum, right? So when I use the trivalence atoms, the outermost shell consists of 3 electrons. available, 3 electrons are available. So therefore, 3 electrons of a trivalence atom joined with the 3 neighboring atoms of a silicon atom, 3 neighboring silicon atom, and then it creates one site for other electron to jump in, right? So this is what I will show you here. Yes. So this is what it shows, right? So this is a trivalence atom, all right, plus 3 is a trivalence atoms, and 3 electrons. So this is 1 electron of this. This is another electron of this. This is 1, 2, and then 3, right? So 3 electron of a trivalence atom joined with 3 neighboring silicon atoms, right? Now this creates a hole, right? This creates a vacancy, and this creates a vacancy, and any electron can jump and occupy this vacancy, and this is what we call as a hole. This is what and this creates acceptor energy level. This creates what we call as acceptor energy level, right? This creates acceptor energy level. That means these atoms accept electron from a neighboring atoms, and then creates negative ions. That's negative ions, negative acceptor ions, negative acceptor ions. So this is what we have. So therefore hole is created. This creates some kind of hole, right? In a way this creates what we call as a hole. This creates a hole, and any electron can jump and occupy this, and leaving behind another hole. Leaving behind another hole. In a way, I can say that 3 electrons of a trivalence atom joined with the 3 other neighboring electron of silicons, and keeping one hole, and any neighboring electron can jump and occupy this space. If I add 10 trivalent atom, this creates 10 holes and 10 vacancy. This can create a 10 vacancy. Any electron from a valence band can jump and occupy this, and there is a transfer of electron, there is transfer of hole taking place in a valence band. So things are taking place in a valence bands. So this is what I have here. So when an atom of a +3 valency element occupy a position of atom in the crystal lattice of silicon, all 3 electrons bond with the 4 neighboring silicon, while the 4th electron of a silicon remain unbounded. And this creates vacancy or hole at trivalence atom. As a result, the ionization energy required to set electron to fill hole is very small. And for germanium, again it is 0.3, 0.01. For silicon it is 0.05. So that means it is like this. This is conduction energy level, and this is acceptor energy level, and this is valence energy level. Alright, so the holes, right, before combination holes are available in the acceptor energy level, and this energy gap is 0.01 for germaniums and 0.05 for silicon. So therefore room temperature this kind of energies are available, so electron can jump and occupy a hole and create holes, right, leaving behind hole. So this is what, and I say this create acceptor ion, this create acceptor ions. So this is what we have. So if I do a trivalence, what you have to understand is this creates acceptor energy level, all right, this creates the acceptor energy level, and then and a hole, right, create a hole in a valence band, and then trivalence atom remains positive, negative ions, negative acceptor ions, create negative acceptor ion, and this negative acceptor ion is this negative acceptor ion is fixed. All right, and this is not supposed to move. It is a hole that moves in a valence band. The hole is the one that moves in a valence band. All right, now having this, I have here. This is what I have, p-type semiconductor. This is what we call as a p-type semiconductor. This is acceptor energy level. This is what we call as acceptor energy level, and this is the valence energy level. And electron can jump into acceptor energy level, energy level even at a room temperature. This is what we have. All right. This is what we have. What we talk about p-type semiconductor. Now this is our textbook diagram. Now in this case, I have put 7 acceptor. I have put 7 trivalence atom. All right. Due to which 7 holes are created. 1, 2, 3, 4, 5, 6, 7. And this hole is created because of thermal excitations. And this electron is created due to thermal excitations. All right. This is acceptor energy level. Look at here now. Now I have a 2 charge carrier. One is this is what we call as electron charge carrier, and this is a hole charge carrier, right? Electron is very less number. Why? Because this is entirely due to thermal excitations, less number, and this has thermal as well as this has a thermal as well as doping, right? By process of doping, right? So therefore, I say hole is what we call as a majority charge carrier. Majority charge carrier, and electron is what we call as minority charge carriers. Minority charge carrier. All right. So therefore, I write here this is very less compared to this. So I told you in case of semiconductor we have 2 kinds of charge carrier. That is a majority charge carrier and a minority charge. In case of a p-type semiconductors, hole is a majority charge carrier. In case of n-type semiconductor, it is the electron that is minority charge, majority charge carrier, and hole that is minority charge carrier. So this is what I have. One more diagram. This is for both p-type semiconductor and n-type semiconductors. This is both for p-type semiconductor and n-type semiconductor. So p-type, n-type semiconductor creates donor energy level, and p-type semiconductor creates acceptor energy level. All right, and n-type semiconductors donor energy level. So therefore, electron available is more. P-type semiconductor hole available is more. So therefore, hole is a majority charge carrier in case of p-type semiconductor, and electron is a majority charge carrier in n-type semiconductor. So this is what we have. Alright, now we would like to discuss one very important concept, or that is what we call as the formation of Pn Junction. Right. So what about if I join p-type semiconductor and n-type semiconductor? This is very important, right? So what happens if I join p-type semiconductor and n-type semiconductors? That you should keep in mind. 3 things will take place. Very important. One is diffusion, and another one is drift, and formation of space charge regions. Formation of space charge regions. Formation of space charge regions. Diffusion current, drift current. Diffusion of electron, drift electron. This is what. So these three things I am going to explain, right? So three important phenomena occur during formation of Pn junction diode. So this is what we have: diffusions and drift and formation. So this is what I have. Now look at here. Before I do this, when I say diffusions, and diffusion is a phenomenon which occurs due to concentration gradients, and the diffusion is a phenomenon which occurs because of concentration gradients. The diffusion, osmosis is a diffusion, right? Because of a concentration gradients, water comes out. All right, it flows from higher concentration to lower concentrations. It goes from higher concentration to lower concentration. Drift is the phenomenon, or this is a flow due to by external push, due to by external force, or due to by external field. So that is what we call as a drift. This is a natural process, and this is the process occur because of applying force. All right, and formation of, and because of which the formation of charge region is there, right? So so what I'm going to do is now, as soon as I join p-type semiconductor and n-type semiconductor, p-type semiconductor has more number of hole, all right, and less number of electrons. N-type semiconductor has more number of electrons and less number of hole. Why? Because the majority charge carrier is hole and the minority charge carrier is electron. Majority charge carrier is electron and minority charge carrier is holes, right? So therefore, as soon as I join p-type semiconductor and n-type semiconductors, diffusion takes place. Why? Because there is concentration gradients. More electron, more hole, less hole. More electron, less electron. So therefore, as soon as I join p-type semiconductor and n-type semiconductor, diffusion takes place. Immediately diffusion takes place. How diffusions? Electron diffuse from N to P. Electron diffuse from N to P. Electron diffuse from N to P. And a hole diffuse from P to N. Because of which it creates, when an electron leaves N, this creates positive ions. Positive ions. This creates a positive ions. Positive ion is created due to movement of electron, right? Electron from N to P, and negative ion is forms. Negative ion is forms. All right, negative ion is forms due to transfer of or movement of hole from electron to P to N. So this is what we have. Because of which now it positive charge region is formed. Positive charge. This is what we call as positive charge region at N site, and negative charge regions, and I'll write here negative charge regions at P site. This is very, very important, and these things are fixed. Immovable. These are immovable charge, right? Because of which electric field is created. Because of which electric field is created, right? Because of this, all right. electric field is created. Because of which electric field is created. Alright? Once the electric field is created, the electron that is minority in a p types dip into n type semiconductors. Electron that is minority in a p type dip into n type, which is what we call as a majority, right? And the hole that is minority in an n type dipped into hole that is dipped into. Alright, this is what we call, right? Alright, so there is when I write here, this is how electric field direction is this. This is electric field directions. This is field directions. This is field directions. Alright, this is field directions. And this electric field brings the minority hole and into a p-type semiconductor, and this will bring a minority electron into a n-type semiconductor. So therefore diffusion is created, and diffusion is already created, and dip is created, and because of which depletion region is created. Right? Depletion regions, positive depletion region is nothing but positive charge regions and negative charge regions. Because of positive charge region and negative charge region, this creates electric field, due to which electrons dipped into n-type semiconductors, hole dipped into p-type semiconductor because of applied so. So after some times, the diffusion current as the electric field increases, diffusion current decreases, diff current increases. So after some time, equilibrium state is reached where diffusion current is equal to diff current, right? Once this stage is reached, what we call it as the equilibrium, right? So therefore, there is no flow of charge taking place. No flow of charge taking place. Now why? Because diff current is equal to diffusion current. Alright, so this is the point. Depletion regions. So why we call depletion region means movable charge is depleted. There is no free charge carriers available. No free charge carriers are available. Free charge carriers are depleted. This is a region where free charge carriers are depleted. This is a region there is no free charge carriers are available. So therefore, this is what we call as a depletion regions. And this depletion region will not allow a hole from p-type to get into a n-type, and depletion region will not allow a whole electron from n-type to get into a p-type. So therefore, the depletion region will create some kind of potential barriers. This creates some kind of potential barrier because of which the further movement of electron from n to p stops, and this stops the further movement of a hole from p to n. So this is how it is formed. This is what I have diagram, right? And once the equilibrium state is reached, we call a formation of a Pn junction diode is done, right? Formation of Pn junction is Pn junction is formed. Why this is red? This is a positive ion. This is a blue. Blue is negative ions, and therefore no movement is created. Right? This creates a potential barrier. This creates a potential barrier. This is again, it is done. P-type semiconductor. This is P-type. N-type movements are created once equilibrium state is reached. So this is positive ions. This is negative ions. This is what we have. Alright, equilibrium is reached. This is potential barriers. So potential barrier is 0.3 to 0.7 volt. For germanium it is 0.3. For silicon it is 0.7. Right. So this is what we had. N-type regions, P-type regions, minus electrons. These are the hole. this is electron. This is a positive ion. This is a positive ion, right? This is not done, right? Plus are hole and minus are electron, right? Okay. So with this. So with this we say that with this I'm going to stop right now. What we have done is we have done with the formation of Pn junction diode. So next class what I'm going to do is we are going to discuss the biasing, right? Forward bias and reverse bias, and then application of Pn junction diode. And last, this is a positive ions. Create a positive potential, negative ions create a negative potential, and this is fixed. You should keep in mind. This is fixed ions that you should keep in mind. This is fixed ions. All right. This is negative electrons, and this is hole. This is electron, and this is hole, and this is depletion regions, and this depletion region creates electric field. This depletion region create electric field, and this electric field, electrostatic fields will not allow movement of electron from N to P and from hole from P to N, and this create what we call as the potential barrier. All right. So with this I'm going to stop. Thank you.